titled Basic Concepts of Chemical Bonding. In previous chapters, we've gained the understanding that it is the nature of electrons and the importance of electrons that gives rise to chemical interactions. Specifically, we're talking about those valence electrons, those electrons on the outermost portions of an atom that are going to contribute to chemical bonding. With that in mind, we need to understand that there are three basic types of chemical bonds, and they differ in the way that the electrons interact with neighboring atoms. The first type is the ionic bond. The ionic bond results from the gaining and losing of electrons. In doing so, we see the formation of ions, positively charged cations and negatively charged anions. It is the attraction between a positively charged cation and a negatively charged anion that is the ionic bond. So the electrostatic attraction between ions gives rise to that type of bonding. A covalent bond involves the sharing of electrons rather than a give and take. The electrons are still associated with each individual atom, but in order to, well, let's just say become electronically happy, we find that the atoms themselves will share electrons rather than gaining or losing. And lastly, we can talk about metallic bonding. Now, the concept of metallic bonding is going to go beyond the scope of our lecture. But please understand, the nature of metallic bonding involves the continuous flow of electrons in what's oftentimes referred to as a sea of electrons. And it is this continuous flow of electrons between metal atoms that make metals conductive, or rather that allows metals to be conductive. Keeping track of all of the electrons in an atom can be quite problematic. For example, the 50 electrons in an atom of 10. If we're talking about a chemical interaction involving 10, it's going to be hard to keep track of 50 electrons and their potential interactions. But the good news is not all of those electrons are going to participate in chemical bonding. If you'll remember from previous chapters, it is the valence level, or those valence electrons, that are instrumental in chemical bonding. And so Gilbert Lewis, a man much smarter than I am smart, developed a method for keeping up with the valence electrons associated with a particular element. In doing so, we see the establishment of what we call Lewis symbols. The Lewis symbol for an element is represented by its chemical symbol and a series of dots, each dot representing one valence electron around that particular symbol. Regardless of the nature of bonding, we're going to find that when forming compounds, atoms tend to gain, lose, or share electrons in an attempt to obtain 8 valence electrons. This is called the octet rule. The word octet suggesting a grouping of 8. In the same way that when 6 people sing, it's a sextet. When 4 people sing, it's a quartet. When 2 people sing, it's a duet. If 8 people were to sing, well, I think you get the gist. We typically characterize ionic bonding as taking place between metal atoms and nonmetal atoms, with the exception being those noble gases. Noble gases already have a complete set of valence electrons, a complete octet, if you will, so they do not participate in ionic bonding. In these interactions, we see that metal atoms typically lose electrons in order to look like the previous noble gas. Nonmetals tend to gain electrons in order to look like the following noble gas. In doing so, metals form cations, nonmetals form anions. And the process tends to be fairly exothermic. In other words, we typically see the release of energy as the result of ionic bonding. That's because the metal atoms typically have lower ionization energies, so they will readily give up an electron. The nonmetal atom tends to have a high electron affinity, or it benefits from gaining an electron, energetically speaking. Below, you can actually see the transfer of the valence electron from an atom of sodium to an atom of chlorine in order to form a sodium cation and a chloride anion. Since each of these ions have a stable electron configuration, the resulting compound, sodium chloride, would be formed. Ionic compounds typically have well-defined three-dimensional structures. We'll see them in repeating arrays of cations and anions. Structurally speaking, we find that oftentimes ionic substances are crystalline, that they are brittle, and they tend to have high melting points. And when they do break, with respect to their brittle nature, that they tend to break or cleave along smooth lines. As I mentioned before, metal atoms tend to lose electrons, and in doing so will obtain an electron configuration of the previous noble gas. Now, that holds true for main group metals. We classify a metal as a main group metal as opposed to a transition metal. Nonmetals tend to gain electrons, and in doing so, they will obtain the electron configuration of the upcoming nearest noble gas. Transition metals, those are the metals that we find on the periodic table between groups 3 and 12. They do not follow the octet rule. When electrons are lost in the formation of ions from transition metals, we see that the transition metals lose the valence electrons first, and then they lose those d electrons in order to obtain the necessary charge. Oftentimes, we will see that transition metals can form ions with multiple charge. For example, titanium can form an ion with a charge of +2 or +4. Cobalt can form an ion with either a charge of +2 or +3. Now, a good portion of our discussion is going to be focused on covalent bonding. In covalent bonding, we see atoms sharing electrons. So I want you to imagine two atoms in close proximity. On the exterior of these atoms, we're going to find the electrons. Tucked way down deep inside the nucleus is where we find the protons and the neutrons. So the electrons from one atom are going to be attracted to the nucleus of the other. But at the same time, if these atoms are in close enough proximity, the electrons on one atom are going to repel the electrons on the neighboring atom. And once again, if these things are close enough, we're going to see the repulsions of the two nuclei. Positive and positive are going to repel. Negative and negative are going to repel. Positive and negative are going to attract. So in order for us to see a covalent bond established, the attractive forces and the repulsive forces have to be balanced out. To speak of covalent bonding and how compounds are formed as a result of these interactions, we can visualize the nature of covalent bonding using Lewis structures. Now, if you'll remember, we talked about Lewis symbols just a few moments ago. Lewis symbols were those designations of atoms of a particular element that also had the number of valence electrons associated with them given a dot or a series of dots. Well, to illustrate covalent bonding, the sharing of electrons, we can use these Lewis symbols in order to form compounds, which will be represented by Lewis structures. Now we start by trying to determine the number of electrons that would be necessary in order for an atom to be, dare I say, electronically happy. When entering into chemical combination, atoms will tend to do so in an attempt to walk away with a complete set of valence electrons. And for most atoms, that is an octet, that is 8. Hydrogen is an example of an element that will only require 2 valence electrons. So the octet rule, when referring to hydrogen, I guess would be more of a duet rule, in that it only requires 2, those 2 electrons filling up the outer valence level that we typically think of as the 1s for hydrogen. Now, if we look below, we see examples for diatomic hydrogen as well as diatomic chlorine. Hydrogen has 1 valence electron. The other hydrogen has 1 valence electron as well. If each hydrogen wants to walk away with 2 valence electrons, then we can see a very simple scenario that might be akin to a handshake. You hold my hand while I hold yours. Well, you can have this electron if I can have your electron. Now, it's not a give and take. Once again, it is a sharing. So each hydrogen atom walks away with the understanding that it has 2 electrons in its immediate vicinity. And that makes each one electronically stable. If we look at chlorine, an atom of chlorine, like all halogens, is going to have 7 valence electrons. In order to obtain a complete set of valence electrons, which would be 8, each chlorine atom wants 1 more electron in order to be completely happy, if you will. So if we have 2 chlorine atoms, each of which is deficient 1 electron towards its goal, if each chlorine atom, once again, decides to participate in this handshake, then we can see the sharing of electrons through what we call a covalent bond that will allow each atom to walk away with 8 electrons in its periphery. Now, it's important for us to remember in general the number of valence electrons associated with each particular group. Those alkali metals, the group 1 metals, things like sodium, potassium, rubidium, lithium, they have 1 valence electron. The group 2 elements, beryllium, magnesium, and the like, have 2 valence electrons. Remember, we shoot past the transition metals, and the group 13 elements, like aluminum, have 3 valence electrons. The group 14 elements have 4 valence electrons. The group 15 have 5, group 16 have 6, group 17 have 7, and the group 18 have 8. But why are we even talking about the group 18 elements? Because they're not going to participate in covalent bonding. Moving on. In order to get to an octet, in covalent bonding, we're going to see nonmetals sharing electrons with one another. And in the simplest example of covalent bonding for nonmetals, we're going to see that the number of bonds needed will be the same as the number of electrons needed to complete the octet. So let's look at things like carbon and nitrogen and oxygen and fluorine, small nonmetal atoms. If carbon has 4 valence electrons, then in order to complete its octet, it needs 4 more valence electrons. If hydrogen has 1 to share, then it would take 4 hydrogens in order to complete the octet around carbon. In doing so, we would see the formation of a compound with the formula of CH4, also known as methane gas. Nitrogen has 5 valence electrons. In order to complete its octet, we would see 3 hydrogens or 3 electrons needed. In doing so, we would see the formation of NH3, also known as ammonia. Oxygen has 2, or is rather 2 electrons away from having a complete set of valence electrons. It has 6 valence electrons and it wants to get to 8. So in order to complete the octet, each hydrogen willing to give 1 electron would see the formation of H2O, otherwise known as water, and fluorine, a halogen that has 7 valence electrons. It only needs 1 electron in order to complete its octet. So if it were, again, in the simplest example of covalent bonding, going to form a molecule with hydrogen, it would only take 1 atom of hydrogen sharing its lone electron to complete the octet. Notice that in each example, hydrogen completes its duet, if you will, by sharing its electron and receiving 1 in return. HF is a compound known as hydrogen fluoride. When dissolved in water, it becomes hydrofluoric acid, and that is a story for another day. Hydrofluoric acid is some bad stuff. Moving on. Now, on the previous slide, we saw that there were a series of electrons that were represented with respect to the Lewis structures. There were some electrons that were placed only on one atom, and then there were electrons that were shared between atoms. Those electrons that are associated with only one atom are called lone pairs, while those that are associated with the bonding, the shared electrons, are called bonding pairs. They are typically represented by 2 dots or a single line. A pair of electrons is represented by a single line. Now, up until this point, our discussion of covalent bonding has only involved the sharing of 1 pair of electrons between 2 atoms. Hydrogen completing the octet around fluorine means that 1 pair of electrons is shared between hydrogen and fluorine. In this instance, 1 pair of shared electrons is called a single covalent bond. But sometimes we're going to see that 2 pair of electrons need to be shared. In the case of 2 shared pair of electrons, we would refer to these as double bonds. And yet still we will find instances where 3 pairs of electrons need to be shared. These are called triple bonds. If you look at the bottom of the slide, you will see that in the formation of carbon dioxide, 1 atom of carbon and 2 atoms of oxygen, if an atom of carbon has 4 valence electrons, then it wants to get 8 in order to be completely happy. Oxygen has 6 valence electrons, so each oxygen is going to want to gain 2 electrons in order to complete the octet. In order to do so, we see the sharing of 2 electrons from each oxygen with carbon. The carbon will in turn share 2 of its electrons with each oxygen, and everybody walks away happy through the formation of double bonds between each carbon and oxygen. At the very bottom of the slide, we will see an example of nitrogen gas. Nitrogen gas in the form of N2 is the primary component of the air that we breathe. And it's in the form of this diatomic molecule, the N2 molecule. How is the N2 molecule formed? Well, each atom of nitrogen has 5 valence electrons. And in order to complete the octet, each one is willing to share 3 of its electrons with the other nitrogen to walk away with a total of 8. Now, if you will note, on each nitrogen, we see a lone pair of electrons and the electrons that are being shared. So since there are 6 electrons, or 3 electrons being shared, 3 pair of electrons being shared between the nitrogens, the result is called a triple bond. Now it's important to note that the sharing of electrons in a covalent bond is not always equal. The term bond polarity is a measure of how equally or unequally electrons are being shared in a covalent bond. Imagine a game of tug of war. If each participant is pulling with the same intensity, then we would see an equal sharing of electrons. But if one is pulling a little harder, then that would represent an unequal sharing of electrons. In a non-polar covalent bond, the electrons are being shared equally. But if the bond is considered polar, it is because one of the atoms is attracting electron density to itself with a greater force. In other words, one of the atoms is winning the tug of war. The electrons are still being shared between the 2 atoms, but they're not being shared equally. In the case of elemental fluorine, diatomic fluorine, a molecule of fluorine made up of 2 fluorine atoms, we see that each fluorine atom is pulling with the same intensity. The sharing of electrons takes place equally. Therefore, the bond would be considered a non-polar bond. But in hydrogen fluoride, the interaction between hydrogen and fluorine, we see that the sharing does not take place equally. Fluorine actually pulls the electron density closer towards the nucleus of fluorine than hydrogen does. If we imagine that the bond itself, the space in between the 2 atoms, has a hydrogen end and a fluorine end, as would be the case with the tug of war, we would see that the electron density would be greater on the fluorine end than it would be on the hydrogen end. That represents a charge distribution between the 2 atoms. The hydrogen side doesn't have a high electron density. The fluorine side has a lot of electron density. So one might go so far as to say that the hydrogen side, being electron deficient, would be slightly more positive. The fluorine side, having a higher electron density, would be more negative. So how is it that we know that fluorine pulls harder on hydrogen than hydrogen does on fluorine in a molecule of hydrogen fluoride? Well, it's through a value known as the electronegativity. Now, electronegativity is the ability of an atom to draw electron density towards itself in a chemical bond. The most prominent electronegativity scale was given to us by Linus Pauling. And on this scale, fluorine is considered to be the most electronegative element there is, having a value, an arbitrary value of 4.0. So everything is less electronegative than fluorine. With that being said, we can see a trend similar to the trends that we saw in chapter 7, a periodic trend with respect to electronegativity. If fluorine is the most electronegative element that there is, then as we go down a group, we get less electronegative. Fluorine is more electronegative than chlorine, which is more electronegative than bromine, which is more electronegative than iodine. Also, as we go from right to left, we would see a decrease in electronegativity. Fluorine is more electronegative than oxygen, which is more electronegative than nitrogen, which is more electronegative than carbon. And I'll stop right there. So by looking at the difference in electronegativity values, we can determine which element is pulling electron density towards it more readily. Since fluorine has an electronegativity value of 4.0 and carbon has an electronegativity value of 2.5, the difference between those two values is 1.5 in the direction of fluorine. Fluorine is pulling harder on those electrons. So we see the formation of a polar covalent bond. We see the unequal sharing of electrons. Now, iodine, on the other hand, has an electronegativity value of 2.5. So if carbon and iodine were to share electrons, since they have similar electronegativity values, then one might say that that is a nonpolar covalent bond. Now, as I mentioned before, in the formation of hydrogen fluoride, we see the electron density being pulled more towards fluorine than hydrogen. And at the bottom of the slide, we see two ways in which we can represent that graphically. We can either, using the Greek letter delta, the lowercase Greek letter delta, which suggests a partial nature, we can say that the particular bond in hydrogen fluoride is partially positive on the hydrogen side and partially negative on the fluorine side, because the electron density is being pulled more towards the fluorine than the hydrogen. We could also use an arrow on top of the bond itself to illustrate the direction of net electron pull. In general, the greater the difference in electronegativity between two atoms, the more polar the bond is, or the greater the polarity. In the table listed below, we see the bond lengths, the electronegativity differences, and a calculation known as the dipole moment of a series of hydrogen halides, hydrogen interacting with the halogens, those group 17 elements. As you might suspect, in going from hydrogen fluoride all the way up to hydrogen iodide, we see an increased bond length. Iodine is much larger than fluorine in terms of its atomic radius. So the distance between the center of a hydrogen atom and the center of a fluorine atom in a bond is going to be significantly smaller than that of the hydrogen to iodine internuclear distance. Now, it should be noted that this bond length is listed in angstroms, a measurement that is equal to 1 × 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ meters or 0.1 nanometers. But as we go from hydrogen fluoride to hydrogen iodide, we see a decrease in the electronegativity difference between the atoms themselves. Since fluorine, being the most electronegative element there is, has a value of 4.0 on Pauling's scale. Hydrogen has an electronegativity value of 2.1. The difference between those two is 1.9. This gives rise to a large charge distribution or a large dipole, on which one end we see positive and one end we see negative. As we go down the periodic table in terms of those hydrogen halides, we see that that electronegativity difference decreases significantly. Iodine, having an electronegativity value of 2.5, is not very different than hydrogen in terms of its electronegativity of 2.1. So we see a very small electronegativity difference, and the charge distribution is not that great. The dipole moment is a calculation that reflects that electronegativity difference, that speaks to the dipole presence in a molecule. Now that we have a basic understanding of Lewis symbols, as well as a grasp on the concept of electronegativity, we can use this information to put together Lewis structures. Given the chemical formula for a compound, how is it that we know what is bonded to what? In a molecule of carbon dioxide, how do we know that it consists of a carbon bonded to two oxygens as opposed to a carbon bonded to an oxygen, which is then bonded to another oxygen? How do we know that in a molecule of water, we have an oxygen atom that is bonded to two hydrogens, as opposed to another bonding scheme? How do we know that in a molecule of phosphorus trichloride, what is bonded to what and how? Are they bonded via single bonds, double bonds, triple bonds? And how do they differ in terms of their bonding from carbon monoxide, from hydrogen peroxide, and from phosphorus pentachloride? Three compounds that are similar in elements to carbon dioxide, water, and phosphorus trichloride, but not necessarily similar in their bonding schemes. Well, we're going to begin our discussion with regards to the rules and guidelines for drawing Lewis structures by considering phosphorus trichloride. Well, the first thing that we need to do is sum up the valence electrons from all of the atoms, taking into account the overall charge. So if we were looking at phosphorus trichloride, we understand that phosphorus, being in group 15, has 5 valence electrons, and that chlorine, being in group 17, have 7 valence electrons. So if we total up all of those electrons, those valence electrons, the electrons that are going to be instrumental in chemical bonding, then we come up with a total of 26 electrons. Now, since phosphorus trichloride is a neutral species, accounting for those 26 electrons is all we're going to need to do in order to draw this structure. If we were trying to draw the Lewis structure of an anion, for example, the hydroxide anion, we recognize that there is an additional electron associated with the atoms that are there. It has the formula of OH minus. So we would have to add 1 electron for each negative charge. For the carbonate anion, which has a charge of -2, we would add 2 electrons to the valence electron total. If we were dealing with a cation, such as the ammonium cation, which has a formula of NH4+, then we would subtract 1 electron. Nitrogen has 5 valence electrons. Each hydrogen has 4 valence electrons, which would bring us to a total of 9. But since it is charged in the form of a cation, that means that there is 1 fewer electron there than we would suspect based simply on the atoms listed. But back to phosphorus trichloride. The next thing that we do is we write the symbols for the atoms, indicating which atoms are bonded to which. And the first thing that we need to do with regards to showing the bonding is to connect them via a single bond. Worst case scenario, they're going to be bonded by a single bond. That's the simplest scenario. They may end up being double bonds. They may end up being triple bonds. But to simply show that they are bonded, we first indicate the bonding via a single bond. How do we know that phosphorus is going to be bonded to the chlorines in the fashion that's shown here? Well, there are some guidelines that we consult when drawing the skeletal structure of a molecule. In other words, what things are connected to what. One of those prominent guidelines suggests that the central atom is going to be the atom which is the least electronegative. So if we consult our electronegativities with regards to phosphorus and chlorine, we see that phosphorus is found to the left of chlorine on the periodic table, which would suggest that phosphorus is less electronegative. One of the guidelines also suggests that atoms tend to adopt a compact structure around a central atom. So rather than think of a phosphorus bonded to a chlorine and that chlorine bonded to another chlorine and that chlorine bonded to another chlorine, we're going to adopt a nice compact structure around a central atom. Now that we've drawn a single bond in between all of the chlorine and phosphorus interactions, we understand that each bond represents a pair of electrons. So now we need to keep track of these electrons. By drawing 3 bonds, we have essentially drawn 6 of those valence electrons. So of the total of 26 electrons that need to be accounted for, we have accounted for 6 of them, with 20 left to dole out. We need to consider the octet rule. When entering into chemical combination, atoms tend to do so in an attempt to obtain the same electron configuration as the nearest noble gas, or obtaining an octet, or 8 valence electrons. So the next step in drawing Lewis structures is going to be assigning the external atoms, what we call the terminal atoms, an octet of electrons with those valence electrons that we're keeping track of. In order to complete the octet around chlorine, we need to add 6 electrons per atom of chlorine. Now, since we've got 20 of them to dole out, by placing 6 electrons on each chlorine, we now have only 2 electrons remaining. Any remaining electrons need to be placed on the central atom. So we place those last 2 electrons on our phosphorus. If we look at our structure as it is, all of the atoms now have a complete octet around them. Each chlorine has 6 electrons in lone pair and 2 electrons tied up in a bonding pair. The phosphorus has 2 electrons in a lone pair and 6 electrons in the 3 different bonding pairs, 1 bonding pair per chlorine. Since all of the atoms now have a complete octet, and we have our central atom being the least electronegative, this would suggest a satisfactory Lewis structure. Now, in the instance where there were not enough electrons to give the central atom an octet, then we may find the need to explore the concept of multiple bonds. And that's something that we will see in just a moment. If we were to put these rules together for the hydrogen cyanide molecule, we would first total up all of the valence electrons. Hydrogen bringing 1 valence electron, carbon bringing 4, nitrogen bringing 5 to the table, giving us a total of 10 valence electrons. If we were to put together a skeletal structure, we would do so with carbon being our central atom, being the least electronegative. Stop. That's not 100% true. Hydrogen is less electronegative than carbon, so why is carbon our central atom here? Well, if we consult those guidelines, we understand that since hydrogen only has 1 electron to share, it can't be a central atom. It can't share with 2 different things. Hydrogen is always going to be a terminal atom. So given the choice between carbon and nitrogen as being the central atom, carbon is less electronegative than nitrogen. So with carbon as our central atom, hydrogen on one side, nitrogen on the other, we would connect those 2 via a single bond, accounting for 4 of the 10 electrons. The next step would suggest that we decorate our terminal atoms, our external atoms, with electrons in order to complete the octet. Well, since hydrogen, once again, already has a complete set of valence electrons with 2, those 6 valence electrons are going to be placed on our nitrogen. So our nitrogen has an octet. At this point, we've run out of electrons to dole out. Yet the carbon does not have an octet. So in order to remedy this, we shift the lone pair of electrons from nitrogen in order to form a bonding pair or a multiple bonding pair between nitrogen and carbon. It doesn't hurt nitrogen. The electrons are still associated with nitrogen. But by attributing them to a bonding pair, it does help establish an octet around carbon. If you look at the structure on the right, you will see that carbon now has 8 electrons around it, 2 in the bonding pair with hydrogen, and 6 in the triple bond with nitrogen. Everybody walks away with a complete set of valence electrons. Therefore, this suggests a satisfactory Lewis structure for hydrogen cyanide. Now, while those rules will be sufficient for many of the molecules that we attempt to draw, in some instances we may find ourselves needing more. For example, in the establishment of the carbon dioxide molecule, the bottom of this slide, we see that there are 2 possibilities for drawing carbon dioxide when we use those rules. We would essentially start with a carbon being the central atom in between 2 oxygens, sharing 1 pair of electrons with each oxygen and 6 electrons in valence electrons as lone pairs around each oxygen. At that point, we would have doled out all of the electrons possible. So we would find ourselves wanting to shift a lone pair to a bonding pair to make the octet around carbon complete. But we would find ourselves asking, do we shift 1 pair of electrons from each oxygen, or do we shift 2 pair of electrons from 1 oxygen to make a single bond carbon-oxygen and a triply bonded carbon-oxygen? Both of those would seem to suggest satisfactory Lewis structures, but there's a way to evaluate which one is the most satisfactory Lewis structure, and that involves assigning formal charges. Now, the concept of formal charge does not speak to an actual charge, but the formal charge is the charge that an atom would have if all of the electrons in a covalent bond were shared equally. Now, we know that electronegativity suggests that all electrons are not shared equally. But by taking formal charge into consideration, we can better evaluate potential Lewis structures to see which one is the most likely. Now, in calculating formal charge, we take the number of valence electrons, total number of valence electrons associated with a free atom. We're going to subtract half of the electrons in bonding pair and subtract all of the electrons in lone pair or non-bonding electrons. If we do so, then we will find that the formal charge on each atom in the first illustration of carbon dioxide is minimized to 0. In the second structure, we will see that the formal charge is minimized to 0 for the carbon, but for the oxygen on the left, the singly bonded oxygen, we have a formal charge of -1. For the triply bonded oxygen, we see a formal charge of +1. So why does this evaluation make one structure more valid than the other? Well, I'll tell you why. The prevalent or the dominant Lewis structure is the one in which atoms have formal charges that have been minimized or as close to 0 as possible. In the previous example, we see that one illustration of carbon dioxide features all of the atoms with formal charges of 0, while the other has a carbon with a formal charge of 0, oxygen with a formal charge of -1, oxygen with a formal charge of +1. The more valid structure would be the one in which all of the atoms have a formal charge of 0. Now, there may be some instances where that's not possible, where all of the formal charges aren't 0. Well, when that is the case, as is the case with the thiocyanate ion listed below, the dominant structure is going to be the one in which the most electronegative element has the negative formal charge. So going through those rules and guidelines for establishing a Lewis structure for the SCN- thiocyanate polyatomic molecule, we see the 3 structures listed below as possible Lewis structures. To evaluate which one is best, we do a formal charge calculation on each atom. In the first structure, we see that nitrogen has a formal charge of -2, oxygen a formal charge of 0, and sulfur a formal charge of +1. In the other 2 instances, we see 2 atoms with a formal charge of 0 and 1 atom with a formal charge of -1. So if we were to eliminate one of these 3 from contention, it would be the first structure, because we have the fewest number of atoms with the formal charge of 0. Now, to determine which of these 2 would be the most valid structure. Well, we're going to place the negative formal charge on the most electronegative element. And when looking at the electronegativities of nitrogen and sulfur, it becomes evident that we're going to assign the negative formal charge to the more electronegative element. Now we're about to explore a different type of bonding scheme in a molecule that we call ozone. Ozone is a triatomic form of oxygen. We're probably more familiar with the diatomic form of oxygen that we breathe in on a regular basis. Ozone is a different allotrope or naturally occurring form of oxygen. Its usefulness is oftentimes referenced to the ozone layer in our atmosphere, which absorbs ultraviolet radiation. But the ozone molecule can be drawn via Lewis structures. It's just perhaps not as straightforward as we might think in terms of its bonding. Well, let's use our rules and guidelines. Our rules suggest that we sum up all of the valence electrons in a molecule. All of the atoms that make up the molecule are oxygens, and each oxygen brings 6 valence electrons to the table, bringing us to a total of 18 valence electrons. Well, now we've got to determine which one is our central atom. Well, it's going to be oxygen. That's it. It's just going to be oxygen. So we connect the oxygens via a single bond. The first structure that is drawn accounts for 4 of the 18 valence electrons. Next, we're going to decorate our terminal atoms with valence electrons to complete their octet. Each terminal oxygen requires 6 valence electrons around it to complete its octet. Now, if we look at the central structure, we have 16 valence electrons accounted for. Our next rule says to add any remaining electrons to our central atom. In doing so, we now see 3 oxygen atoms, 2 of which have a complete octet, but the central only has 6 valence electrons around it. It does not have a complete octet. Well, before, when we experienced such an issue with hydrogen cyanide, we decided that we were going to take a lone pair of electrons from one of the terminal atoms and shift it to a bonding pair. My question to you is, which oxygen? Do you shift it from the one on the left to make a bonding pair to complete the octet around the central oxygen, or the oxygen on the right? If we assume that all 3 of them are distinct atoms of oxygen, then we have to treat them that way. And understanding that the bonding between the oxygen on the left and the central atom, and the bonding of the central atom and the oxygen on the right, represent 2 different electronic environments. So how do we know which oxygen to shift the lone pair of electrons from? Well, we do it from both. We make 2 different structures, one in which we see shifting from the left, one in which we see shifting from the right, and then we compare the formal charges. Well, if we were to do so, we would find that each of the structures shows 3 atoms of oxygen with formal charge distributions that are similar. So how do we determine which structure is right? And more importantly, is either one of them right? Well, regardless of the structure that we draw, regardless of which lone pair of electrons gets shifted to a bonding pair, it would appear that our final structure is going to involve an oxygen double bonded to our central oxygen and an oxygen single bonded to our central oxygen. So 2 different types of bonds between our oxygens. But when we look in actuality at the bonding of ozone, that doesn't necessarily agree with our calculations. The bond distance between the central oxygen and each of the oxygens turns out to be 1.278 angstroms. Now, it's not important what that value is, but it is important that both of the values are the same. So the bonding scheme between the central oxygen and each of the terminal oxygens must reflect similar bonding. Well, how is that going to be the case? If in fact one of them is a double bond and one of them is a single bonds are longer than double bonds. So how are these 2 bonds equal in bond length? Well, the simplest answer is both. The Lewis structure is not one or the other, but both Lewis structures are equally valid. When we find multiple Lewis structures that are satisfactory and give equal formal charge distributions, we observe a condition known as resonance. One Lewis structure cannot truly depict how the molecule exists. It's actually a blending of both. The electron density is being shared throughout the molecule through what we call delocalized electrons. Each structure represents what we refer to as a resonance structure, and they combine to form what we call the resonance hybrid. It's as if one structure were the color yellow and the other structure was the color blue. If we ask what the true structure looks like, yellow or blue, the correct answer is neither. It looks like green. So it's neither one nor the other, but it is both. The organic molecule known as benzene, with the formula of C6H6, has two structures that would be considered resonance structures. When you draw the Lewis structures for benzene, and I recognize that the drawing of this indicates a ring structure that we may not be familiar with just yet in terms of the carbons bonded to one another. The point of it is, we can draw two separate structures with bonding schemes that will reflect similar formal charge distributions throughout all of the atoms present. Now, when we began our discussion of drawing Lewis structures, we referred back to the octet rule, the idea that when entering into chemical combination, atoms tended to do so in an attempt to walk away with 8 valence electrons. But it is important to note that there are exceptions to the octet rule. There are instances where the octet rule is not possible for various molecules. 3 such exceptions involve ions or molecules with an odd number of electrons, ions or molecules with less than an octet, and ions or molecules with more than an octet, or more than 8 valence electrons. There are instances of molecules and ions with an odd number of electrons. If we consider nitrogen monoxide, we will find that a total of 11 valence electrons are present, 5 of them coming from nitrogen, 6 of them coming from oxygen. And there's no way that you can draw a satisfactory Lewis structure in which the octet rule is satisfied for all atoms with 11 valence electrons. If we consider nitrogen to be our central atom, being the less electronegative, then the structure on the left would suggest that we bond it via a single bond, decorate the oxygen with an octet, place any remaining electrons on our central nitrogen, and since at that point our central nitrogen would be electron deficient, we would shift a lone pair from the oxygen to form a bonding pair with nitrogen. At that point, our nitrogen would have 7 valence electrons around it. Any other shifting would increase the number of valence electrons around nitrogen to greater than 8. And nitrogen is not one of the elements that can hold more than 8 valence electrons. So the structure listed on the left would be the prevalent or the dominant Lewis structure. The Lewis structure drawn on the right does speak to this same idea, but you will notice the difference between the two in evaluating the formal charge distribution on each. In the case of the left, the nitrogen has no formal charge. On the right, the nitrogen has a formal charge of -1. The oxygen has a formal charge of +1. So on the left-hand side, we see the formal charges minimized, which would suggest, once again, that that is the satisfactory Lewis structure, even though a complete octet cannot be achieved around all elements. Now, it is for this reason that we find molecules with an odd number of electrons to be extremely rare and highly reactive. That lone electron wants to form a pair with something. Next, we see an example of a molecule in which the central atom has fewer than 8 valence electrons. If we consider boron trifluoride, which by far is the most prominent example of this exception to the octet rule, by drawing the structure for boron trifluoride using those rules and guidelines, we would see 24 total electrons that need to be accounted for, with boron being the less electronegative element. It's going to be our central atom. Each fluorine as a terminal atom is going to be bonded to the boron with a single bond. That accounts for 6 of the valence electrons, with 18 left to dole out. If we put those 18 valence electrons around our terminal atoms, those are all of the electrons that we can assign to this molecule, which would appear to leave our boron with only 6 valence electrons around it. Now, in the past, what we would do is we would take a lone pair from a fluorine and then shift it to a bonding pair. But there's a problem in doing that. If you do so, and then do a formal charge calculation, you will find that the fluorine that you just shifted an electron pair from in order to make a double bond is now going to have a formal charge of +1, as opposed to a formal charge of 0 if you were to have left it alone. That means that fluorine was going to lose the tug of war with boron for that double bonded pair of electrons. And if electronegativity is a measure of the intensity with which electrons draw electron density towards them, then it's pretty unbelievable that fluorine is going to lose the tug of war with anybody. Fluorine is the most electronegative element there is, so it's not going to lose that tug of war. Even though we can draw 3 different resonance structures that would reflect that bonding. In each instance, we see a fluorine that is electropositive in that we see a formal charge distribution that would suggest +1, while boron's formal charge would be -1. And that's not likely. Now, there is evidence to suggest that those 3 resonance structures do exist, but they are not the dominant form of boron trifluoride. The dominant form, the most prevalent form, is the one in which the octet rule is not satisfied. So, in short, if filling the octet of the central atom results in putting a negative formal charge on the central atom and a positive formal charge on a terminal atom that is more electronegative, just don't do it. Just don't do it. It will be content with a central atom with fewer than 8 valence electrons. The final exception to the octet rule lies in ions or molecules that have more than 8 valence electrons around the central atom. This can occur when the element in question is found in period 3 or beyond. Periods 1 and 2, we will not see this type of behavior, but we can see it beginning with elements in period 3. For example, we started our discussion of drawing Lewis structures with phosphorus trichloride, a molecule in which all atoms saw the octet rule satisfied. But there's another molecule involving phosphorus known as phosphorus pentafluoride, in which we see phosphorus not obeying the octet rule. It turns out that if we were to draw the structure for phosphorus pentafluoride, we would have to put phosphorus as our central atom, being that it is the least electronegative. And the 5 fluorines would have to bond to something that wasn't another fluorine. So they all have to bond to our phosphorus. In doing so, we find 10 valence electrons around our phosphorus. If we use the remainder of our 40 total valence electrons to decorate the terminal fluorine atoms, we will obtain the structure that we see on the bottom left-hand side. Now, while it looks to be an extreme violation of the octet rule, our first inclination might be to throw it out as a valid Lewis structure. But if you evaluate the formal charge distribution on all of the atoms present, even the phosphorus has a formal charge of 0. So with formal charges of 0 across the board, and understanding the nature of elements in group 3 and beyond, we see the possibility of using d orbitals to hold additional electrons. And we only see that starting with period 3. These molecules can be considered to be hypervalent in the environment around the central atom. On the bottom right-hand side, you will notice the phosphate anion, an initial attempt to draw the phosphate anion. We'll have single bonds between all of the oxygens and the phosphorus. You'll notice that the formal charge distributions involve -1 on all of the oxygens and a +1 on the phosphorus. We can further minimize the formal charge distribution on a single oxygen and on the phosphorus by shifting one of those lone pairs to a bonding pairs. If you look at the structure on the right, it appears to be more minimized in terms of the formal charge distribution. And therefore, we would suggest that it is a more valid Lewis structure, even though the phosphorus is hypervalent, taking on more than 8 valence electrons. The final portion of this chapter is dedicated to the concept of bond enthalpy. Enthalpy, if you'll remember from our chapter on thermochemistry, speaks to the energy associated with a particular process. And if we're talking about bond enthalpy, it is essentially the energy that is required to break a particular bond. Since that's going to be a very small value, we typically refer to the molar enthalpy, or the enthalpy associated with breaking 1 mole of a particular bond. At the top of the slide, you will see what is akin to a chlorine molecule, 2 atoms of chlorine bonded via a single bond. And the energy associated with breaking a mole of that particular bond is the bond enthalpy of chlorine. At the bottom, we see a molecule of methane, which involves 1 atom of carbon and 4 atoms of hydrogen. In order to break those bonds, we would also speak to the bond enthalpy. The process of breaking bonds requires energy. Therefore, the bond enthalpy values are going to be positive. Now, Breaking a carbon-hydrogen bond in methane might require a different amount of energy than breaking a carbon-hydrogen bond in another molecule. So when we see these values listed in table form, these are typically averages of bond enthalpies over many compounds. Since energy is required to break bonds, the reverse process must release energy. When bonds are formed, we see energy released. So the greater the bond enthalpy, the stronger the bond. The greater the bond enthalpy, the more energy is required in order to break the bond. And in forming a new bond, the more energy will be released, the stronger the bond. Here we see a table of average bond enthalpy values. If you'll note in the first column, we see the energy associated with breaking a mole of carbon-carbon single bonds is 348 kilojoules per mole. The energy associated with breaking a mole of carbon-hydrogen single bonds is 413 kilojoules per mole. It should be noted that the energy of breaking a carbon-carbon double bond is greater than that of a carbon-carbon single bond. Well, that would suggest that a carbon-carbon double bond is indeed stronger than a carbon-carbon single bond, which makes sense if you think of more electrons between the two atoms means more of an attraction, more of a glue holding these atoms together. If we were to look at the energy associated with a carbon-carbon triple bond, we would see that that energy would be greater still. Carbon-carbon single bonds are longer but weaker than double bonds, which are longer and weaker than triple bonds. We can see a similar trend in the third column where we look at the oxygen-oxygen bond enthalpies. Here we see a correlation between bond enthalpy or bond strength and bond length. If we take into consideration the series of nitrogen-nitrogen bonds that can form, we find that a nitrogen-nitrogen single bond is the longest, while a nitrogen-nitrogen triple bond is the shortest. Does that make sense? Well, if we consider the atoms in question having electrons between them in terms of bonding electrons to glue them together, the nitrogen-nitrogen single bond doesn't have as many electrons as the nitrogen-nitrogen triple bonded scenario. The more electrons being shared, the tighter the glue, if you will, the closer the nuclei are going to be to one another. So the triple bonded nitrogen, while it does represent the strongest bond in terms of bond enthalpy, it also represents the shortest bond in that the nuclei are really, really close to one another. So in conclusion, we determine that multiple bonds tend to be stronger than single bonds. But in making that statement, we have to understand the elements in question have to be comparable. For example, we can't say that a carbon-oxygen single bond has a particular relationship to a nitrogen-nitrogen double bond. We can't compare single bonds to double bonds that way. We can say that a carbon-oxygen single bond is weaker than a carbon-oxygen double bond. We can say that an oxygen-oxygen single bond is weaker than an oxygen-oxygen double bond. But we can't compare the strength of a carbon-oxygen double bond to a nitrogen-oxygen single bond. With that being said, single bonds are longer and weaker than double bonds, and double bonds are longer and weaker than triple bonds. I'm sorry, folks, I didn't make it up. That's the law. Ba-dum-bum-tsh. Also, for different bond types, we understand that the bond energy or the bond enthalpy is not going to be the same for a carbon oxygen bond in one molecule as a carbon oxygen bond in a different molecule. We can measure an average bond length for these various bond types. And as the number of bonds between two atoms increases, the bond length decreases. Thank you for your time and have a great day.